with a 20 to 25% external quantum efficiency. But the issue here is still we can improve the efficiencies if we can suppress the non-radiative, the emissions from the singlets and triplet states. And simultaneously, there is another the mechanism which has proposed is hot exciton TADF. This is similar to the traditional TADF, except the difference between the two mechanisms is in the case of hot exciton TADF, the upconversion can also occur from the higher excited states. In the traditional TADF, we expect the upconversion from the lowest triplet state to the singlet states. But in the case of hot exciton TADF, the upconversion can occurs from the preferably from the higher excited states. So in order to achieve these conditions, it has to obey some conditions. So what I'm going to do today is by taking some examples, we demonstrate how what are the important factors that one can should keep in mind while designing TADF materials to achieve both traditional TADF mechanism as well as hot exciton TADF mechanism. So let me start with the traditional TADF emitters, which is basically we used quinoline based donor acceptor molecules as the TADF emitters. This we got inspired from the recent experimental study, which is published in the Chemical Engineering Journal, in which they have taken a fragment of fullerene, which is also called quinoline, which is a bowl-shaped organic molecule, pi-conjugated molecule. What they have done is they have fused a donor unit to the quinoline unit, and they have studied the TADF properties of these molecules. As you can see on this bottom of this slide, it has a small singlet triplet gap with the reasonable reverse intersystem upconversion. So these results are really encouraging. So we want to explore these materials by choosing different donor and acceptor combinations, as well as to improve the reverse intersystem crossing uh, rates. So we start with what is the impact of donors. So we have considered 5 different donors. These donors are uh, dihydrophenazine and phenoxazine and carbazole based donors. So in the case of when we take but as the strength of donor is decreasing, the homolumo gap also increasing. But important fact that also we observed is in the case of phenazine and phenoxazine based donors, you can see the clear separation between HOMO and LUMO wave function delocalization. So in order to achieve the small delta EST gap, we should we should avoid the HOMO-LUMO overlap. So the larger separation between HOMO-LUMO results the smaller delta EST. So, but when we take a carbazole or carbolane based donors, we have seen a good overlap between homolumo wave functions. So, as a result, you can see a large gap between singlet triplet gaps, which hampers the rates of reverse intersystem crossing. But the important point you can also observe here, even though these carbazole and carbolane based donors has the large delta EST, they obey very strong spin orbit coupling between singlet and triplet gaps. So this is kind of a trade-off. In order to have the faster reverse intersystem crossing, we should have a strong spin orbit coupling with the decent energy gap between singlet triplet states. So by keeping in that mind, we have chosen a wide variety of donors with a different strength of donating capability and different acceptors, which with a different alpha in nature. And we have considered quinoline has the pi bridge here. We also kept another fact in our mind when we choosing these acceptor molecules. We have done the literature search, and we have chosen the acceptors which are already reported with the quinoline. So these are experimentally not difficult to synthesize. So these are the 15 new molecules that we have designed with the different combinations of donors and acceptors. As you can see from these optimized geometries, the donor is almost perpendicular to the uh, pi bridge here, the coronal molecule. So we can expect a direct separation between homo-lumo wave function and as well as a smaller energy gap between singlet and triplet states.
क्योंकि मेरा बहुत पसीना
So
निकल
you can
रहा
see here, I have shown only one
था
case here. These are the phenoxyzine-based
मिक्स हो गया था
donor molecules with the different types of
हम्म
acceptors, like benzene to sulfoxyline-based acceptors. Depends upon the strength of
हमको आपको
acceptors. We
क्या हो
can see
जाता है
here how
कि जितना
LUMO
लेट
energy
में
level
सोगा
is fluctuating.
नींद खुल
The
जाएगा वही
stronger
टाइम और
acceptors,
जल्दी
the
सोएगा फिर
deeper,
भी वही
the
टाइम
deeper
तो
LUMO.
सोचा लेट ही
But in
सो
all the cases, the
लेकिन
donor is,
जल्दी सोना
I mean,
अच्छा
since
होता है
it has the same donor,
मैं
the
देख रही हूँ
HOMO
मैं
energy
खुद
levels
है
are
देख
more
रही
or less same. The fact here is it depends upon the strength of acceptor that we choose. We get the different homolumo gap, because these homolumo gaps are directly I mean, correlated with the
दाग भी
absorption,
कम हो
light
पता है वो
absorption
हेल्दी
ranges.
होती है
You
मेरे
can
पास
see here the out of
आप
15
खा रहे थे
molecules
सुबह
depends upon the strength of donor and acceptor. The absorption ranges are varies from 400 nanometers to
लेकिन मुझे भी
the
ऐसा
near a
लगता
year
है कि मैं
range of
फील की
950
कल
nanometers.
बहुत हुआ
So a rational design between, I mean choosing of donor and acceptor, we can design the emitters with the different ranges.
वाइट
But unfortunately, this is not sufficient, because the main principle of TADF, I mean the rates of reverse intersystem
ये तो
crossing, is mainly depend upon two factors, as I mentioned: the spin orbit coupling between the singlets and triplet states, and the energy gap between the singlet and triplet state. So we have measured these parameters for the all 15 molecules, and we have calculated the rates I mean, we have observed 10 to the power of 7
ओह ओके
ranges
ओके
in
ये तो
most of
हमारा भी
the all
बनता है 14
molecules,
तारीख
except in the case of
के
carbazole
ये अप्रैल को
based donor molecules. As I mentioned, in the case of carbazole based donors, they suffer from the large singlet triplet gaps, even though they have exhibited very strong spin orbital coupling values. So we are trying to
पता है
understanding
इसको चालू
how can we
कहते
balance
जैसे कुछ
this
बात था
spin
क्या
orbit coupling and the energy gaps. So hopefully we will end up with some new system which has the stronger spin orbit coupling with the very less singlet triplet gap. And also, I also want to show how the torsion angle between the donor and pi bridge impacts the performance of these molecules. So I have considered two systems here, again phenazine and phenoxyzine based
ओहो
molecules. When we twist the angle between the donor and pi bridge around 15 degrees, it crosses the around 1 kilocalories of
अच्छा
energy barrier. But as you can see, in the case of phenazine, there is not
ये
much change
बात
in
है
the rates of
तो
reverse center system crossing. But in the case of nitrogen based donor, we almost lose twofold the rate. So even a small change in the structure, that means 15 degrees striatal angle change between the donor and acceptor, energetically it is very very small. I think everybody can appreciate this. The at room temperature, we have zero point 0.6 kilocalories
कुछ माइंड करता
from the KT. So this is very very small number, and we can expect such a disorder in the organic molecules, which can hamper the reverse center system crossing rates. So while designing the
45
molecules,
46
not only the energy levels of the molecules, we also try to design the molecule which has more rigid structure, so that we can avoid the structural disorders in the molecules, and also we can without losing the
सब
rates
होता
of
है
reverse intersystem crossing. The next part, I'm going to talk about the hot exciton based TADF molecules. So as I mentioned, this in the case of hot exciton based TADF molecules, the intersystem crossing occurs at higher energy levels. So generally, in the case of traditional TATF, we worry about the lowest singlets and lowest triplet states. But in the case of hot exciton reverse intersystem crossing, there is a large gap between T1 and T2 state. So it suppresses the internal conversion. So before there is an internal conversion occurs, the charges converts to the singlet states. So the overall conditions to have the hot exciton TADF mechanism is, the first condition, it should have a large energy gap between T2 and T1 state so that we can suppress the internal conversion. And we also should have a smaller energy gap between singlet and triplet states so that we can up convert the charges from triplet state to the singlet states, not only from the one channel. Here we have a many channels. In the case of traditional TADF, we mostly rely on S1 and T1 states, but since if we can design a molecules which has a smaller energy gap between higher singlets and higher triplet states, we will have a many potential channels uh, with the up conversion. But the great difficulty associated with such molecules is, it is very difficult to design molecules with a large energy gap between T2 and T1 states, and at the same time we should have a smaller energy gap between higher singlet states and higher triplet states. So in the case of the traditional TADF molecules, we have only one issue, that we try to maintain a small energy gap between S1 and T1 state. But here, in order to have a more efficient hot exciton mechanism, if we get more benefit if we have a smaller energy gap between the singlets and triplet states. So this is the main potential challenge while designing the molecules with respect to hot exciton TADF mechanism. And also we get extra beneficial if S1 is a LE state. So if S1 is a LE state, it will be it could be we have a narrow emission spectrum with a stronger S1 radiative transition. So if one can keep all these facts while designing some molecules, we can have a potential molecules for hot exciton TADF. So we have adopted a molecular design strategy in which a donor and acceptor is flanked between a benzene ring as well as a pi bridge here. So we have chosen two different donors, carbazole and again phenazine based donor molecules, and we have considered thiazole containing naphthalene and anthracene units as the pi bridge, and we have considered three different acceptors to tune the homo-lumo energy levels. So with these combinations, we have designed around 15 molecules. And the most attractive part of this designing strategy is, as you can see from the picture, it has a very effective conjugation across the molecule from the donor to acceptor. So we can really control the energy levels while depends upon the donor and acceptor that we choose. So these are the optimized geometries are of the molecules that we have designed. Again, like in the previous case, here you can see here there is a twist between the donor unit and the pi bridge, which ensures that these sufficient separation between homo and lumo wave function for the smaller singlets and triplets energy gaps. So we have studied the lowest 10 singlets and lowest triplet states, and we have identified among all the molecules, only three molecules obeyed the first condition. The first condition is having a larger T1, T2 gap. So we have taken these three molecules for the further evaluation, and what we have observed is of all these three molecules, carbazole has the donor unit and anthracene based thiodiazole as the pi bridge. So we considered carbazole, and this pi bridge is a potential choice for the designing hot exciton based TADF emitters. So we have studied in detailed, study of these energy levels so that we can identify the potential channels for us these three molecules. So for example, in the case of the first molecule, we have identified two potential channels, that is from S1 to T2 state and S2 to T4 states. We have identified these channels based upon two factors. One is a strong spin orbit coupling and the larger separation between singlet and triplet energies. So it depends upon the molecule. In some molecules, we have identified three or four potential channels, and in some molecules, we have identified two or three. Depends upon the strength of spin orbit coupling as well as energy gap. So the whole idea is, again, the rates are depends upon the spin orbit coupling and the energy gap. As you can see here, the moderate choice of the moderate donor and the moderate acceptor has shown the stronger rates of
काय ग डाटा
reverse intersystem crossing compared to the strong acceptor. Anyway, we do
आम्ही
not have a strong donor here. When we consider a
नाही की
strong donor,
ते
we
डबल
couldn't
किती
achieve
लावली होती
larger T1 T2 energy gap. So the overall conclusion that we have understood from this
सांगलं काय
study is, in order to have a hot exciton TADF, we should choose a weak donor with the weak acceptor. So when we take a weak acceptor, again we may not get the sufficient reverse intersystem crossing. So the moderate acceptor could be a ideal choice to achieve a faster reverse intersystem crossing, so that we can have an efficient uh, uh, OLED system. So the overall key points that we have established from the both the traditional TADF as well as hot exciton based TADF is, we have shown some potential strategy for designing these molecules. The combining strategy of having a large T1 T2 gap, a smaller singlet triplet energy gaps in the higher states with a larger spin orbit coupling would achieve the hot exciton process in the organic molecules, and a combination of weak donor with a moderate acceptor is necessary to achieve faster, higher reverse system crossing rates. So I would like to acknowledge our university for the financial support, also DST Inspire and DST NSM for the support with
एक
respect
क्वेश्चन
to
मारते का
the
पूरा सारा
computational resources. And
27
I also would like to thank the PhD student
हाँ
Chesney Jacob to carrying out all these calculations.
तेरा
And
बच्ची
I'm
को
glad to
रिचार्ज
take
करके इसलिए
if
मैं
you have
दीदी
any
को ज्यादा
questions.
मेरा भी 2 रुपए ज्यादा जियो से जियो वाले से अच्छा फोन पे से लेता है ना शाम का क्यों इनको 2 रुपए ज्यादा देना काय ना
Any questions
Yeah,
or
yeah.
comments?
Thank you, Makesh Kumar, for very nice presentation. So have you?
जल्दी खत्म
So
कर
these are our calculation, right?
Yeah, these are all critical
Did you
and
get to check with the experimental thing? Did you get a chance to?
yeah, actually the motivation behind choosing these molecules from the experimental studies, as I mentioned in the talk.
और सबको
Mhm.
क्वेश्चन पूछते हैं
So we when we adopt the designing
मतलब
strategy,
भी
we
सबको
make
क्वेश्चन
sure
पूछते
that
हम चलो
we do
मैसेज
not choose the molecules which are impossible to synthesize.
Okay.
I'm not sure these molecules are exist in the literature, but these are doable.
Okay. So for the art excite on TADF, do you
Yes.
think that will
बोल मोबाइल नंबर
can reach the performance maybe
मोबाइल
similar
नंबर
to
था
the
82
conventional TADF design?
Yeah,
65
yeah. Theoretically, it should, because
0513
in the case of traditional TADF, as I mentioned, we have only one potential channel. But in the case of hot exciton
ये
TADF, we
268
have many potential channels. So theoretically, we should get a higher external
02
quantum
बराबर है
efficiency.
1362
But if you see the literature, experimental studies shows that
58
the hot exciton TADF external quantum efficiency is much lower than the
04
Yeah.
traditional TADF. So we have to study
बोलो तो जाना बात
carefully why, I mean, such losses is happening. So
Actually,
that,
what we feel
like
like
after
maybe under electrical excitation,
yeah,
maybe T2 to T1,
लपड़ा जो
that
होता
transition may be much faster than
है मैंने फोन
yeah,
पे
that,
स्टार्ट करूँ
because it has to spin, has to flip to
किधर
come
से
to
एक मिनट तो
singlet
आएगी
state,
ना
right? We feel
yeah.
that maybe it's very difficult. Maybe under electrical excitation, this transition may be very fast.
Yeah, that is a really good point. That is what, I mean, when we are submitting the paper, we that is also one potential question that we expected from the reviewer. As I'm not denying it, the rates of internal conversions are really competitive with respect to the rates that we are calculating
सर
for
तू किराया रही
reverse and system crossing.
तू क्या रहा
But I mean, as I mentioned,
ये उतना ही पैसे देगा
I think it is doable if you carefully design the molecule with the